All right, get ready, because today we're going to tackle something pretty wild: quantum entanglement. It's one of those things in physics that's just so bizarre. It even made Einstein a little uneasy, to say the least.
Yeah, and the really wild thing is this isn't just some theory anymore. Quantum entanglement is a proven thing. It's so big that in 2022, a Nobel Prize in Physics was awarded for work on it.
I know, right? To break this down, we've got this awesome YouTube video by Barry Sheskin. He's great at taking these complex topics and making them actually understandable. So I guess what we're trying to do today is figure out what quantum entanglement even is, why it's so mind-blowing, and what it could mean down the line.
Sounds like a plan. Let's jump in.
Okay, picture this. We've got two boxing gloves. One gets sent to Niels Bohr over in Copenhagen. The other goes to Albert Einstein in Princeton. Now, until they open those boxes, neither one knows which glove they have.
Right, it's a 50-50 chance, kind of like what we see in the quantum world.
But here's the thing. The second someone opens one box, they instantly know which glove is in the other box. No matter how far apart they are, it's like the gloves are talking to each other across the globe.
That's a good way to think about entanglement. It's not just about knowing which glove is where. There's an actual connection between the gloves at a subatomic level. They're linked, even over huge distances.
Okay, I'm seeing the quantum connection here, but are these tiny particles really connected across, galaxies?
In the quantum world, particles can get entangled, meaning their fates are tied together. If you measure something about one particle, you immediately know the same thing about its entangled partner, even if they're light years away.
So it's almost like they're communicating faster than the speed of light. This is already messing with my head.
Not exactly communication as we know it. To get this, we got to talk about something called superposition. Think of a spinning coin. It's not heads or tails until it lands, right? Well, quantum particles, they exist in this fuzzy state of multiple possibilities all at once.
So you're saying these entangled particles haven't decided what they are until someone looks at one. And that forces the other one to instantly become the opposite.
That's a good way to put it. This uncertainty, the superposition, is at the heart of entanglement. It's like they're connected by this invisible string, no matter how far apart they get.
Gotcha. Definitely strange, but also pretty cool.
Mm-hmm.
No wonder Einstein wasn't a huge fan. Didn't he call it spooky action at a distance?
He did. He wasn't comfortable with it because it seemed to go against his theory of relativity. You know, the one that says nothing travels faster than light. He figured there had to be something else going on, them hidden variables, things we haven't discovered yet, that could explain this seemingly impossible connection.
So he thought it was more logical than that. There had to be a reason that fit with our everyday experience.
Yeah, he believed that each particle's properties were already set even before we measured them. There's that famous quote, "God does not play dice," meaning he thought there was no randomness to it. It was predetermined.
But if everything was already set, wouldn't that clash with the whole entanglement idea? I mean, it seems like things are only decided when we look at one of the particles.
Exactly, that's the core of the debate. And this disagreement really shook things up in the physics world. Back in 1935, Einstein, along with Podolsky and Rosen, they wrote this paper questioning if quantum mechanics was really complete. They argued that it must be missing some pieces to explain these spooky connections.
So they were saying quantum mechanics as it stood was flawed, that there was more to the story.
Exactly. This paper, called the EPR paradox, said there had to be these hidden variables messing with things.
So how did other scientists react to that? Did anyone try to debunk the EPR paradox?
Well, Niels Bohr, another big name in quantum mechanics, he quickly jumped in to defend the theory and its weirdness. He insisted there weren't any hidden variables and that quantum mechanics was a complete picture of reality, even if it seemed counterintuitive.
So Einstein and his crew argued for these hidden variables. And Bohr stood his ground, saying quantum mechanics was all we needed. Sounds like an epic science showdown. But how could they ever settle this? It seems like a philosophical debate more than a scientific one.
For a while it was, but then in the 1960s, a physicist named John Bell came along, and he really changed the game. He actually figured out a way to test for these hidden variables.
Wait, he brought the debate from philosophy to actual testable experiments? This John Bell guy sounds like a real revolutionary.
Oh, he absolutely was. Bell, being a bit of a rebel himself, had his own doubts about quantum mechanics. Initially, he kind of leaned towards Einstein's thinking. But his big breakthrough was this theorem, now called Bell's theorem, that gave us conditions we could actually test in experiments.
So how'd that work? Did he invent an experiment for these hidden variables?
Remember our analogy with Alice and Bob receiving entangled particles? Bell's idea was to have them ask the particles not just one question about their properties, but two. If the particle states were preset by hidden variables, like Einstein believed, the connections between Alice and Bob's measurements would fall apart when they asked these extra questions.
So if the answers were preset, the particles wouldn't be able to handle the extra questions. But if they could still coordinate their answers, that would mean spooky action at a distance was real.
You got it. This was a game changer. It meant scientists could test the very foundation of reality to see if the universe really played by the strange rules of quantum mechanics.
This is amazing. It's like Bell's theorem cracked open this whole new chapter in understanding quantum entanglement. But did anyone actually do those experiments to test his theorem? What happened next?
Well, that's where things get even more interesting. And that's a story for the next part of our deep dive.
Okay, so last time, we left off with John Bell and this theorem. That could actually test if Einstein's hidden variables idea held any water.
Yeah, Bell's theorem really set the stage for some incredible experiments.
So did anyone actually take on that challenge? I'm dying to know if they proved Einstein right or wrong.
Well, back in 1967, there was this physicist, John Clauser. He was looking through physics journals at the library, and he stumbled upon Bell's theorem and got totally hooked on the idea of proving those hidden variables actually existed.
So he was on Einstein's side, hoping to bring back some order to the universe.
You could say that Clauser was brilliant and ambitious. He saw a real chance to make a mark in physics. He designed this whole elaborate experiment to measure the properties of entangled photons, these tiny particles of light.
And what did he find? Did his experiment back up Einstein's idea?
The results were pretty surprising, to put it mildly. Clauser's experiment was strongly hinting that there weren't any hidden variables after all. The correlations between the entangled photons matched perfectly with what quantum mechanics predicted. It was a big win for Bohr and all those who believed in the weirdness of the quantum world.
Wow, so it seemed like Einstein was wrong. Case closed.
Not so fast. Clauser, being the meticulous guy he was, wanted to be absolutely sure. He realized there could be loopholes in his experiment, sneaky ways that hidden variables could still be at play without showing up in the results.
Loopholes? Like what kind of loopholes?
One of the big worries was this thing called the locality loophole. Basically, it was the possibility that the entangled particles were somehow chatting with each other faster than light, which of course would go against Einstein's theory of relativity.
Ah, so maybe there was this hidden connection we couldn't see that made the particles look linked even if they weren't really entangled?
Precisely, and to deal with this loophole, another brilliant physicist came along, Elaine Aspect, in the 1970s. He designed an even more sophisticated experiment specifically to rule out any faster-than-light communication between the entangled particles.
So Aspect's experiment was like a second, super strict test of Bell's theorem.
Exactly, and guess what he found? Aspect's results backed up quantum mechanics once again. There was no sign of hidden variables or any sneaky faster-than-light shenanigans. This was another big hit to the idea that the universe runs on predictable, local interactions.
Okay, so two separate experiments, both supporting quantum mechanics. Looks like the evidence is stacking up against Einstein, but were scientists totally convinced?
Well, Clauser and Aspect's experiments were huge, but some physicists were still debating other possible loopholes and limits of the experiments. They wanted to be completely certain to rule out every other explanation. And that's where Anton Zeilinger and his team come in.
Zeilinger, he was the one with the experiment in the palace basement, right? What made his experiment so special?
The location was definitely unusual. They set up shop in the basement of the Hofburg Palace in Vienna. But what really set Zeilinger's experiment apart was how carefully it was designed. They built it specifically to address those remaining loopholes and put the debate to rest once and for all.
So they wanted to settle the score in style.
Yeah, you could say that. They sent these entangled photons through fiber optic cables over several kilometers, making absolutely sure the particles couldn't communicate during the measurements.
So they basically created a foolproof test, no more loopholes.
They did everything they could to make it foolproof, and the results. They matched the predictions of quantum mechanics once again. No hidden variables in sight. The weird, non-local connections predicted by quantum entanglement were the real deal.
Wow, after all those years and all those experiments, it seems like the universe really is stranger than we thought.
It definitely seems that way. The experiments by Clauser, Aspect, and Zeilinger, each building on the last, they finally confirmed that quantum entanglement was real and challenged our deepest beliefs about how the world works. Their work was so groundbreaking, they won the Nobel Prize in Physics in 2022.
It's amazing how one simple question, are there hidden variables, led to these massive discoveries. It really makes us rethink what we know about reality. But if these particles can be linked like that, can we actually use entanglement? Could we build technology that takes advantage of this connection?
Now, that's a great question, and it leads us to some of the most exciting research happening in quantum physics today. We'll explore those potential applications in the next part of our deep dive.
I'm already hooked, but for now, let's let all this sink in for a bit. We've traveled through the history of quantum entanglement, from Einstein's doubts to those groundbreaking experiments that proved him wrong. And when we come back, we'll dive into the exciting world of quantum technology and see how this mind-blowing phenomenon could shape our future. Welcome back to our deep dive on quantum entanglement. It's been a wild ride so far, from the basics to those experiments that proved it's real.
Yeah, we've seen how quantum entanglement really throws a wrench into how we think the universe works.
Totally mind-bending. But now I'm thinking, what can we actually do with this stuff? You mentioned some possible applications earlier.
Right. One of the most exciting areas is quantum communication. Remember how when you measure one entangled particle, it instantly affects the other one, no matter how far apart they are?
Yeah, that was the part that really fried my brain.
Well, scientists are looking at how to use that to create super secure communication channels. It's called quantum key distribution, or QKD.
You mentioned QKD briefly before. Could you break down how that works?
Sure. Imagine you want to send a secret message to a friend. With QKD, you and your friend would first need to share a secret key, like a string of random bits that you can use to encrypt and decrypt the message.
So the key is like a code book that only the sender and receiver have.
Exactly. And the cool thing about QKD is that this key is generated using entangled particles. Let's say you and your friend each get one particle from an entangled pair. By measuring certain properties of these particles, you can create a random sequence of bits that only the two of you know.
Okay, but how does that make it secure? Couldn't someone intercept those particles and figure out the key?
That's the genius part. Because of how entanglement works, any attempt to intercept those particles or eavesdrop would mess with their state. And that disturbance would be detectable, so both you and your friend would know the key's been compromised.
So it's like a built-in alarm system for your secret code.
Exactly. That's what makes QKD so secure. It's practically impossible to intercept the key without getting caught.
That's incredible. It sounds like something straight out of a spy movie.
Yeah.
But besides secret messages, are there other things we can do with quantum entanglement?
Oh, absolutely. Another area with huge potential is quantum computing. Quantum computers use entanglement and superposition to do calculations in a totally different way than regular computers. This allows them to tackle problems that are way too complex for even the most powerful supercomputers we have now.
So they're like supercomputers on steroids.
You could say that. They could revolutionize fields like drug discovery, materials science, and artificial intelligence. Imagine designing life-saving medicines, creating new materials with crazy properties, and developing machines that are truly intelligent.
It sounds like quantum computing could change everything, but are these computers even real yet?
They're still in the early stages, but things are moving fast. Building a working, reliable quantum computer is a huge challenge, but scientists and engineers all over the world are working hard to make it happen.
I can't wait to see what they come up with. It feels like we're on the verge of a whole new technological era. But stepping back a bit, what does all this mean for us on a philosophical level? What are the bigger implications of quantum entanglement?
That's a great question. It really forces us to think about what's real. It suggests that the universe might be way more connected than we ever imagined, challenging our ideas about things being separate and independent.
You mean like how we think of objects as being distinct from each other?
Exactly. Quantum entanglement seems to say that at the most basic level, everything is connected. It's a pretty profound and kind of unsettling thought.
It definitely makes you question how we see the world. What other philosophical questions does entanglement bring up?
Well, some philosophers argue that it has implications for free will. If the universe is fundamentally interconnected at the quantum level, does that leave any room for real choice or free will?
Well, hold on. Are you saying our choices might be predetermined by this entangled web of the universe?
It's a complex and controversial debate. There's no easy answer. But entanglement definitely adds another layer to our understanding of free will and whether things are predetermined.
It seems like the more we learn about quantum entanglement, the more questions pop up.
That's the beauty of science. It's this endless search for knowledge and understanding. Every discovery opens up new questions, pushing us to explore further and deeper into the mysteries of the universe.
And it sounds like quantum entanglement has opened up a whole new universe of possibilities, both in technology and philosophy.
Absolutely, from unbreakable codes to super-powered computers and these mind-blowing philosophical questions. Quantum entanglement has the potential to reshape our world in ways we're only starting to imagine.
Well, this has been an amazing journey into the world of quantum entanglement. I feel like I've learned so much, and I'm sure our listeners have too.
It's been great exploring this with you.
Thanks for joining us on this dive into the quantum realm. We hope it sparked your curiosity and inspired you to learn more about this incredible phenomenon that's challenging our understanding of the universe and our place in it.